This video is an overview of the functionality of CBeam. CSection Plus and CBeam, or CSB, is a package of two numerical tools devoted to the computations of homogeneous or composite sections and beams. The present video implies that the first video about CSection Plus has already been viewed. For the classical beam theory, a beam is practically assimilated to a one-dimensional body. This very simplistic view is insufficient to describe the three-dimensional character of the real mechanical behavior of a thin-walled profile or a composite beam for which the materials are strongly contrasted or anisotropic. As shown by the 3D deformed shape of these homogeneous and composite profiles computed by CSB, this package provides a real 3D vision for beams. For CSB, a beam is considered as a slim 3D body for which the cross-section is free to warp or deform in its plane and out of its plane. In CSB, the computations are free from all the classical beam assumptions. CSB allows a real 3D analysis of the beam mechanical behavior in terms of displacements and stresses. To start, let's specify what is done by each one of these two numerical tools, CSection Plus and CBeam. For a given beam problem, CSection Plus is devoted to the computation of the mechanical characteristics of the cross-section, and then CBeam uses these sectional characteristics to compute the beam under any loading and boundary conditions. These tools are developed on Matlab platform and can be used as Matlab tools. Their graphical interface are designed to be immediately and easily used by any engineer or technician. For a given beam problem, the computation time is about a few seconds on a common PC. Using CSB doesn't need particular theoretical or numerical knowledge apart from the usual knowledge about sections and beams or strength of materials. How does the CSB package work? For a given beam problem, the computations need two steps. CSection Plus computes by 2D FEM a large set of mechanical characteristics for the cross-section, and then CBeam uses these sectional characteristics to compute the beam by 1D FEM according to the very recent and advanced beam theory. To do that, the sectional characteristics needed by CBeam are the sectional deformation modes of the cross-section in its plane and out of its plane. These are the Poisson's effects and the distortion in the plane of the section and the warpings out of the plane. This approach, which uses 2D computations for the section and 1D computations for the beam, is very economic and leads to 3D results really comparable to those obtained by a full 3D FEM computation of the beam. As illustration of these results, let's start by a significant example. The example is a short cantilever beam whose cross-section is a thin, open and asymmetric sandwich section. The materials are isotropic and the rate of the Young moduli is 20. The loading is composed by two distributed forces that lead to a torsion and a double bending. One can note the location of one of the loading acting on the right edge of the upper flange of the profile. This example is significant because its complexity leads to believe that it is inaccessible to a beam theory. Its computation requires going through the two steps CSection plus to get the characteristics of the cross-section and then CBeam to compute the beam. This slide shows the CSection graphical interface. The cross-section has already been defined and computed. In particular, the sectional deformation modes have been obtained. Here are, from top to bottom, 7 distortion modes, 3 out-of-plane warpings, and 3 Poisson's effects. These 13 sectional modes will be systematically used by CBeam to compute the beam according to the advanced beam theory. Here is the CBeam graphical interface. The user begins by inserting the section computed by CSection plus, and then CBeam uses the section to generate the beam by extrusion with respect to the beam axis. This is done using the Z coordinates provided by the user. For the loading, the beam is considered as a 3D body, and the loading has to be given as it is, a 3D loading. To declare a clamped section, it is possible in CBeam to block not only the translations and the rotations of the section, but also its deformation in its plane and out of its plane. Once the loading and the boundary conditions have been introduced, the beam can be solved. For comparison, CBeam offers two solvers: ABT to solve the beam according to the advanced beam theory, SVBT to compute the beam according to the classical beam theory. In that case, the in and out conditions are ignored. In fact, SVBT computes the beam according to the Saint-Venant beam theory. Whatever the theory, the computation time is about a second. Here is a comparison of the 3D deformed beams obtained for each one of the two resolutions. For the classical solution, note that the initial section presents an important out-of-plane warping. The curvature of the beam is outwards, and the shape of the free section is unchanged. For the ABT solution, the beam shape is more realistic. There is no deformation of the clamped section, which generates a different curvature for the beam, and the free section presents a clear distortion that reflects the location of the load. Now, here is the comparison of the axial stress distributions sigma ZZ right to the clamped section. Because of the restrained warping, the stress distributions are quite different, and the maximum value of about 800 for the classical theory becomes around the twice for ABT theory. One can show that these 3D results, displacements and stresses, are quite comparable to those obtained by a full 3D FEM computation of the beam. This clearly shows the quality of the results that can be obtained using the advanced beam theory. The presentation of this example will end here because it was aimed to show how a beam problem is performed by the package CSP and to give a good idea of the 3D results that can be obtained. Now it's time to clarify what is exactly the advanced beam theory used by CBeam. As any higher order beam theory, ABT is based on the following displacement model, which has two terms: X and Y being the sectional axis and Z the beam axis. The first term corresponds to the rigid motion of the section, where u and omega are the parameters of the sectional translation and rotation. The second term is an enrichment that allows the deformation of the section. This enrichment uses a combination of sectional deformation mode Mk supposed to be known, and where the amplitude of each mode is controlled by a parameter beta k. This kind of displacement model, using 6 plus k degrees of freedom for the cross-section, allows to better satisfy the boundary conditions. For ABT, the sectional deformation modes Mk are those determined by CSection plus and extracted from the computation of the 3D Saint-Venant solution. ABT is then a higher order beam theory whose originality is to use as modes the own modes of the cross-section, those that reflect the physical nature of the section, shape and materials. For a given section, CBeam generates systematically the corresponding displacement ABT model and then computes the beam by 1D FEM. CBeam is developed to run regardless of the number of modes, since this number can vary from one section to another. Thus, in ABT, we can say that the displacement model, and hence CBeam, fits the section. Now, what about the loading and the displacement boundary conditions in CBeam using ABT? In CBeam, the loading has to be introduced in a 3D way as it is applied and localized on the beam. It is possible to introduce punctual forces or distributed forces per unit length, surface or volume. CBeam ensures automatically the correspondent 1D sectional forces needed by the 1D FEM computation. The displacement boundary conditions act on each sectional parameter of the displacement model. Thus, it is possible to block any component of the sectional translation, the sectional rotation, and it is also possible to block by in the whole in-plane deformation of the section or by out the whole out-of-plane deformation of the section. This allows prevent any deformation right to a clamped section, for example. For a given problem, the computation of the beam is achieved by 1D FEM. The 1D solution is then used to generate the corresponding 3D solution. This is done in a systematic way by CBeam, using the expression of the displacement model, and then the 3D strains and stresses are deduced at any point of the beam according to the classical relations. Note that for a composite section, the elasticity tensor K varies from one material to another. Now, what about the quality of the 3D results provided by CBeam? The enrichment of the ABT displacement model, which includes 6 plus k degrees of freedom, using as sectional deformation modes the own modes of the section, leads practically to a 3D solution that goes beyond that of Saint-Venant, including a significant part of the edge effect. This advantage allows ABT to perform relatively short beams. The 3D results provided by CBeam are quite comparable to those obtained by a full 3D FEM computation of the beam, and this in the major interior part of the beam, even if the beam slenderness is small. This ends the presentation of the key points of the advanced beam theory ABT used by CBeam. To conclude, CSB package proposes a new vision for sections and beams that allows to recover the 3D reality of the beam. CSB computations are completely free from all the classical beam assumptions. They refer to the 3D Saint-Venant solution extended to composite sections and the recent and advanced beam theory ABT. CSection Plus and CBeam are developed as tools of Matlab. They allow quickly and easily predicting a 3D solution quite comparable to that obtained by 3D FEM and can handle relatively short beams. These tools constitute a real help for section and beam design, particularly for the analysis of the inward profiles or composite beams. The current version of the package CSB is limited to static analysis, but future releases will provide vibration and buckling of beams. This completes the video dedicated to the presentation of the package CSection Plus and CBeam.